So next up, we're going to look at optimization problems involving exponential functions. So consider the following function on the closed interval a to b. So this would be a, and somewhere over here would be b. Highlight the absolute minimum and absolute maximum points for this function. We'll hopefully see here we have an absolute maximum. And over here we have our absolute minimum. So that's this point here and this point here. Highlight any local minimum or local maximums. So this one here, you note, is also considered a local maximum. It is a maximum within this region here. We have a second local maximum here, and we have a local minimum here. Now these points, this is not a local min, and this one is not a local min, because our definition of a local max or local min is when you change from increasing to decreasing or decreasing to increasing. And notice at these points there's no change in the direction of the function, so these last values are also called endpoints. Again, we have an absolute maximum here, an absolute minimum here. We have a local max, and a local min. And then we have our two endpoints at x equals a and at x equals b. So let's say I didn't have a picture of this graph. How could I determine the absolute extrema or absolute max or mins for this function without its graph? So here's the algorithm we're going to use. If a function has a derivative at every point on this closed interval a to b, we're going to calculate the height of the function, or what we call f of x or y, at all points on the interval where the derivative equals 0. So wherever the derivative equals 0, so let's go back to our picture. So that's here, here, and here. The slope of the tangent is horizontal. We're going to sub those into f of x and determine the height of the graph at those points. And we're also going to determine the height of the graph at the endpoints. And whichever one is the greatest y value, that'll be our absolute max. And whichever one is the lowest y value, that'll be our absolute minimum. So let's go through an example where we can use this algorithm. So example 1, determine the absolute maximum and absolute minimum values for f of x on the closed interval -5 to 5. So first of all, let's take the derivative for our function. So f prime of x, we're going to use the quotient rule. So p prime of q is going to be 1 times 2 to the exponent of x minus pq prime, so that's x plus 5 times 2 to the exponent of x times ln 2, all over 2 to the exponent of x all squared. So next I'm going to factor out 2 to the exponent of x, and I'm left with, so again I'm taking this out and this out, I'm left with 1 minus x plus 5 times the natural logarithm of 2, divided by 2 to the exponent of x all squared. Cancel where we can, and we have 1 minus x plus 5 natural logarithm of 2 all over 2 raised to the exponent of x. So first we're going to determine where f of x equals 0. So if we solve for this, I get 1 minus x ln of 2 plus 5 ln of 2 equals 0. If I isolate for x, I get that x ln of 2 is equal to 5 ln 2 plus 1. Oops, and I made a mistake here. This should be minus. So this should be 1 minus 5 natural logarithm of 2. And therefore x is equal to 1 minus 5 ln of 2 over the ln of 2. Which, if you evaluate this using your calculator, you should get that x is approximately equal to -3.5573. So now, using where the derivative equals 0 and the endpoints, let's determine the absolute max and absolute min values for this function. So all we're going to do is we're going to evaluate f at -5, that's our first endpoint, f at negative 3.5573, this could be a turning point, and f at positive 5. So all you're going to do is sub these into the original function, x plus 5 divided by 2 to the exponent of x. If we sub in negative 5, we're going to get 0 for our first value. If I sub in the decimal number, I'm going to get 16.98 approximately. And f at 5 is going to give me 5 over 16. So you can see here, this is going to be our absolute minimum. And here is our absolute max. So our minimum is 0. That's the lowest value we get on this closed interval. And our maximum value is 16.98. So the graph looks something like this. So here it passes through x equals negative 5, comes back down, and I think it looks something like this. So here's our point at negative 5. Here's our point where x equals negative 3 point something, the max. F of 5 is somewhere here, 5 over 16. So let's go to our second example. The concentration in milligrams per liter of a chemical in the bloodstream T hours after it's injected is given by the following function. Determine the maximum concentration of the chemical and when does this occur. So taking our derivative, c prime of t, we get e to the negative t, and using our chain rule, that would be times negative 1, minus e to the negative 3t, and using our chain rule, that would be times negative 3. So this tells us we have a derivative equal to 3 e to the minus 3t minus e to the negative t. So again, let's determine where the slopes of the tangents are horizontal. So if c prime of t equals 0, then we get that 0 is equal to 3 e to the negative 3t minus e to the negative t. For this one, I'm going to common factor. So I'm going to take out an e to the negative 3t, and this gives me 3 minus e to the positive 2t. So you might be asking how I got that. Well, e to the negative 3t, if I'm going to factor out an e to the negative 3t, that's going to equal 1. So that's this part here. And then e to the negative t divided by e to the negative 3t. That's e to the negative t, if we subtract the exponents, minus negative 3t, so that's plus 3t, and that's how we got e to the positive 2t. All right, next step, let's solve for where the derivative equals 0. So e to the negative 3t cannot equal 0. And here we get e to the positive 2t is equal to 3. And if we solve for t, we get 2t is equal to the natural logarithm of 3, and t is equal to ln of 3 divided by 2. Notice in this example I wasn't given endpoints. We're going to take 1 point to the left of ln 3 divided by 2 and 1 point to the right to see if that's a max or a min. So let's say I take the concentration at 0. What does that equal? Then I want to compare it to the concentration at ln of 3 over 2, our critical number. And then let's say I just pick here the concentration at ln of 3. Concentration is 0 is 0. If I sub in ln 3 divided by 2 into my function, I get 0.3849. And then if I type in ln 3 into my function, I get 0.2963. So in this one, we see we have our max at ln 3 over 2. So it asks, what is the maximum concentration and when does it occur? And our final example. The effectiveness of studying for an exam depends on how many hours a student studies. Some experiments show that if the effectiveness, E, is put on a scale of 0 to 10, then the function E of t is given by the following expression, where t is the number of hours spent studying for an examination. If a student has up to 30 hours, how many hours are needed for maximum effectiveness? So same as the last two examples. Let's first determine where this derivative equals 0. So e prime of t. Notice this constant here, I'm just going to leave where it is, but I'm going to take the derivative of everything within the brackets. So the derivative of 10 is 0. Then I have plus Now I'm going to use the product rule for t times e to the exponent of negative t over 20. So that's going to be 1 times e to the negative t over 20 plus t, again, times e to the exponent of negative t over 20, then times the derivative of the inside, or the exponent, that's negative 1 over 20. So let's simplify this expression. So I get 0.5 times, well, I'm going to factor out the e to the exponent of negative t over 20, and that leaves me with, so if I take this out and this out, I'm left with 1 minus t over 20. All right, now we just need to determine where does this equal 0. So our first factor, e to the minus t over 20, we know that can't equal 0. That's an exponential function. And for this factor, we get 1 minus t over 20 equals 0. And if we solve for t, we get time is equal to 20 hours. So now that we know where the slope of the tangents equals 0, we now need to evaluate the effectiveness at our endpoint, e equals 0, at our possible turning point, e equals 20, and at our other endpoint, e equals 30. So using your calculators, for 0 I get 5, for 20 I get approximately 8.7, and for 30 I get approximately 8.3. And therefore, the maximum effectiveness occurs after 20 hours. So therefore, So therefore, 20 hours of studying are needed for maximum effectiveness, based upon this model. Try the following questions from your textbook, and good luck.